Oh, fancy seeing you here. I'd like to tell you all about the work kinetic energy theorem, which states that energy is either lost or gained when work is being done. And because of this, we can set them equal to each other. Let's try and find a nice little equation that might help us out. Alright, this one is a little more complicated, so stay with me. It's called the work energy theorem. If you take a look at the equation, it says that work is equal to the change in kinetic energy. Remember, this little guy means change. But we already have an equation for work, and we have an equation for kinetic energy. So let's put them all together. Work is force times distance, and kinetic energy is 1/2 times mass times velocity squared. Easy enough, right? Let's see if we can't plug it into an equation. So, how fast does a 3.0 kilogram block of ice move if 6 newtons of force pushes it 4 meters? Okay, so we're looking for a speed. What do we know? We know that it has a mass of 3 kilograms, it has a force of 6 newtons, and it has a distance of 4 meters. Okay, well, let's take care of this. Yes? Yes. So, force times distance is equal to 1/2 mass times velocity squared. We have a force of 6 newtons times a distance of 4 meters, which is equal to 1/2 of the mass, which is 3 kilograms, times the velocity, which we don't know, squared. Stay with me. 6 times 4 is what? That's right. So we have 24 on this side. What's 1/2 of 3? Correct? 1.5 times velocity squared. Now all we need to do is a little bit of algebra. Let's divide both sides by 1.5. So it cancels out over here. 24 divided by 1.5 is about 15, which is equal to v squared. Of course, we got to get that out of the way. How do we do that? Square root. Take square root of both sides. The squared and the velocity cancels out. And what do we get for a square root of 15? I'll let you guys take a second to look at that one. Done yet? Okay, correct. Velocity is 3.87 meters per second. It's a little more tough, but I think you guys can do it.
One thing I can tell you is you got to be free. Come together right now over me.
The concepts of energy and momentum actually do have a lot of similarities, but they also have a lot of differences. Now, some of the similarities are that both are properties of moving things. You can tell that by both of their equations. Kinetic energy involves a velocity, as does momentum. Some of the differences between them are that momentum is a vector quantity, and therefore is directional and can be canceled, as we remember last chapter. Kinetic energy, however, is a scalar quantity, meaning it can't be canceled. It's just a magnitude.
So, the conservation of energy says that energy cannot be created nor destroyed, only transformed from one thing to another. So to demonstrate that, I've brought in some batteries, some alligator clips, and a light bulb. So I'm going to show you exactly how energy is conserved. So, in the batteries, inside the batteries, there's a whole mess of chemicals rolling around in there, which is defined as chemical energy. Now, when I attach the alligator clips to these batteries, and then attach them again to the light bulb, what we should get
Now, you've all heard of machines before, right? We rely on them every day for even the simplest of tasks. But what you may not know is that they come in 6 basic types of machines. So, one of those machines I brought up is a lever. Now, a lever you might easily have known maybe a crowbar or a seesaw. Those are both excellent types of levers. And so it rotates on a point of support called the fulcrum. It allows a small force over a large distance to be transferred to a large force over a shorter distance. Now, if you look at the equation on the screen, we've seen that before, back when we dealt with Newton's second law. And as one goes up, the other goes down. And so if you'll look at the input work, you're pushing a greater distance with a smaller amount of force. And then to the right, you'll see the output work. It moves a very short distance, but with a lot of force. So they're inversely related. So let's go check it out. Alright, so I'm going to take this crowbar using a small distance with a great force. I'm going to use this crowbar to give a small force over a large distance and transfer it into a large force over a short distance. So all you really have to do is get underneath it and lift it up. Okay? A short distance, greater force. Big distance, smaller force. It's science. A pulley is a simple machine just like a lever. As I said, what makes a pulley interesting is that it changes the direction of the force. So as your input force on the rope is downwards, the output force on the object is upwards. Of course, it wouldn't be a simple machine unless it made work easier. So if it is a standard pulley with 2 arms, the work would be twice as easy. If there were 3 arms of rope, it would be 3 times as easy, and so on. A great example of a pulley is a simple curtain and drawstring. So if you take a look, the entire thing is actually operated by a pulley. So as you pull the string down, the curtain goes up. It changes the direction of force, as a simple machine should. Easy as that! So I'm sure you've all heard before from your parents or maybe your teachers that you're not always very efficient with your time. Maybe a few too many video games instead of homework? Well, efficiency is actually a scientific term that measures the percentage of work you put into a machine and how it's converted to amount of useful work you get out of a machine. So if something is, let's say, 90% efficient, it's probably pretty good. But if something were, say, 20%, you might want to consider tossing it. There's actually a pretty easy way to figure this out back in the classroom. So why don't we get to it? Welcome to the very last calculation of the energy unit. It's all about efficiency. How efficient are the machines that we're using? In order to figure that out, we have a nice little equation. The energy that you get out of a machine divided by the energy that you put into a machine tells you exactly how efficient it is. So if we look at a problem, how efficient is a machine that puts in 1,000 joules of work and only gives out 400 joules? Let's pick out what we know, of course. We know that we have 1,000 joules of input and we have 400 joules of output. All right? So if efficiency is equal to the energy output divided by the energy input, we know it has an output of 400 joules and an input of 1,000 joules. Okay. 400 divided by 1,000 is what? That's right, 0.4. Now, in efficiency, remember, we deal with percentages. What percent of this machine is efficient? And so 0.4 times 100 gives you what? I couldn't hear you. That's right, 40%. That's the unit. The unit for efficiency is percent. So, what this answer is telling us is that this machine is only 40% efficient. Does that sound very efficient to you? It's iffy. All right? Congratulations. That's the last calculation. Give yourself a pat on the back.
I wanna be the sledgehammer. Why don't you call my name?
So energy comes in many different forms, but the strongest by far is right above me. More energy from the sun hits Earth in 1 hour than all the energy consumed by humans in an entire year. Now we can harness this through different things like solar panels, which turn light into electricity. There are wind farms that turn wind into electricity. We can pretty much harness energy from most things in nature.
Energy. Sometimes I think I'm running out of energy. Seems like we use an awful lot for heating and lighting and driving, reading and writing and jiving. Energy. You'd think we'd be saving it up. Energy. You can get it by damming up a river. Energy. A windmill can make the breeze deliver. But even with milling and damming, our needs are so much more demanding. For energy, we have to use some kind of fuel.